Pardon? Hi. You presenting the class name? Yeah. What is your name? I don't have it now. If you have a flash, yes. Yeah, if you want, you can use that one just to like bring it.
Yeah.
Sorry. No. To dig through your flash drive.
No, it's not. It's just
this
actually
one?
for this one. Yes.
Okay. No, it's totally okay. Morning, oh my god, it's on.
Here, that's yes. Why they
Yeah,
change
we're
the
going
name?
to.
It's
So
okay.
this one I just used it. Yes, the old one. So I can. Cool. Everyone is changing slides now. I have love Are you good? You trying to? I can open up the file if you want to check.
Oh, sure. Yeah, it should be in.
Heat map? Okay, that's what you wanted? Lovely, okay. It's a 12-minute presentation. We will put these on your podium at 3 minutes left, 1 minute left. Please wrap up in the next 30 seconds, sort of thing.
You will have to use the control, and there is a list.
So it's just next. No, it's because I unplugged it.
And we will be some kind of letting you know
Yeah, so this is down. There's a laser pointer if you're holding on to the button. It's not the best, yeah.
it will be 9 minutes.
The session
When
doesn't
we
have
will
enough.
be 9 minutes, we will show.
You wanted to change the slide? No. Yeah, so you will fit.
How's everything going in here?
Good. Just updating some last minute slide changes. So
Okay.
figuring that out.
Do you have any virtual presenters, or are they all in person for this time?
I think we have.
Okay.
I don't like
Might be on this.
I'm just uploading some new slides. Sorry, it's just lagging on me.
You're going
I think everyone's.
That would be a process because it's all hooked up to the live stream as well. So I don't want to unplug any of this.
What we are looking is
我们那个人在线，就是有一个 president。
it's a non-business.
But on, sorry, in the other room, usually here it says virtual. I don't see any virtual. I don't think any of them are virtual. They're in mute now and saying that.
Not this
Okay. Okay. There we go. This one. And you're all loaded up.
Keep an eye out.
Copy it.
If something changes, okay? So for the moderator,
Yeah, I know I'm working on it. Good.
Oh, yeah.
Yeah, Amanda, Sylvia, yeah, James, John.
Five? Okay. Cool.
We are all set.
Awesome.
Okay.
Just gonna go check on the other.
Thank you.
guys now. Okay.
So no virtual.
Okay.
Perfect.
So
Do you want me to run the mic and do questions, or do you want me to?
I can do questions if you want a break.
Survey.
I can do questions if you want a break.
I'm happy either way. I just am cognizant that you guys should know this about me. So I'll. So you guys sit up here and I'll sit.
Are you sure?
I'm happy with anything. Just tell me what to do.
oh yeah. I'm not sure if there is enough space for chair.
You can do questions if you want.
Well, I'm happy for you guys to, like, I'm seriously very happy to see you guys. So let's do that. That's
Which one want to do introductions if I have questions? Or? Okay, sounds good.
So we just remember times.
We have five. We're all good.
I'm sorry, what? Yeah, we have. Yeah.
So you can do questions. I can look for Brian.
Is everything open?
Hello.
Hello. Oh, my phone number?
No. I mean phone.
Okay.
I don't need it.
Like, you want my phone number? Okay. So what's that order? Just presenting first? Podium.
Yin.
Yeah, maybe you can just introduce him.
Okay. I can introduce, or I can just introduce. Yes, we can.
You just go to the podium to introduce them.
Okay. So yeah, I just checked. How to turn off these lights?
I think it's all around us.
Okay. Hello, everyone. Let's start part 2 of this session, and welcome to the first speaker, Yilong Huang, which is from University of Alberta.
Alrighty. Okay, cool. Thank you, everyone. My name is Yinglong Huang. I am a second-year PhD student from University of Alberta, and today my topic is modeling regional hydrology, crop yields, and soil phosphorus dynamics in Nelson River Basin. So, as we all know, the Canadian agricultural watersheds, especially those ones in the West, are among the most important breadbasket of the entire world. And the Western Canadian watersheds, they're demonstrated in this brownish area here, have exported to crops to other countries, to over 170 countries in the world. And even Alberta itself would export to over 110 countries every year. So in these globally important regions, the phosphorus limitation is projected to further increase in the future. So when I say phosphorus limitation, I mean the phosphorus limitation in the soil, not in the water body. So that can undermine the soil nutrient balance and consequently would probably impair the food production, the carbon fixation, and the water quality. So, however, the phosphorus cycling, the availability, and the export are driven by various interrelated and dynamic processes, which are very unique to cold regions. And it is immature to make a conclusion that it's just going to simply be, limited. And it necessitates more sort of detailed investigation because, first of all, the freeze and thaw cycle. This is a very unique cycle in the mid to high latitude regions, such as a very long non-growing season and constantly experiencing such cycle. And the cycle would regulate the inflow-outflow processes of soil nutrients. And there are many field-based and empirical studies have already demonstrated on the release of soil nutrients and that impacts on the crop yield, as well as the cold temperature impacting the biogeochemical reactions. And then during the melt season, the snow melt runoff can vary and then transport the soil nutrients. Especially when we're talking about soil phosphorus, they're mostly concentrated in soil on about top 30 centimeter, 15 centimeter. So it's very easy to be transported. Now, on top of that, the soil phosphorus cycling in this region is also controlled by other hydrologic parameters, such as, like I said, snow melt, also soil moisture, soil temperature, etc., etc. So these can sort of, in fact, impact the soil phosphorus pool during non-growing season and its availability for the following growing season. And then, therefore, the amount of fertilizer will be impacted. So with a changing climate, there is an indication of an increased frequency and intensity of the midwinter air temperature anomalies, and that would cause a severe change in the freezing and thawing cycles, as well as the snowmelt processes, which can then affect the soil temperature, the soil biogeochemical and physical parameters, and all of them would eventually impact the phosphorus cycling and its availability to the growing season plant uptake or the exports to the water bodies. So in this context, the ultimate, the ultimate goal of this project is to improve and advance the existing calibrated model of the Nelson River Basin, which was done by a former PhD student in our lab, and then to predict the effects of climate change and management practices on soil phosphorus cycling, and the effects on crop production and export potentials from this, globally important region. So to achieve this goal, my first objective is to take the Red Deer River Basin, which is located on the upstream catchment of the Nelson River Basin, and then to develop a process-based model to understand the phosphorus processes using some improved modules. So I am using SWOT model, the Soil and Water Assessment Tool, and in this model we have a collaboration with a team from the US who have improved the soil carbon cycling, nitrogen cycling, phosphorus cycling, and also the soil temperature simulation. So now here is the area. This is our study area, and it's being located on the upstream of this Nelson River Basin. So this area is mainly dominated by rain-fed crops. And in my case, I am looking at canola. So I'm going to take canola at this moment. So the area is about 47,000 square kilometers, and it's a very typical semi-arid cold region climate. So, like I said, I just talked about the SWOT model, which is the soil and water assessment tool. So basically in this model, you can consider the phosphorus pool into two major categories, the inorganic ones and the organic one. And then each of them are further divided into three subpools, which sort of sets up a either slow or quick equilibrium between each pools, and also simulates the processes of the inflow and the outflow. So in order to calibrate a model, this is a rather sophisticated calibration process, so I'm just going to briefly introduce. I have calibrated a model against the stream flow, crop yield, soil available phosphorus, and soil temperature. So if you have any question later, I can answer you about the details of each calibration processes. Now let's jump into some of the key findings. So I'm going to start off with the non-growing season. So basically, this is a long-term average of snowmelt during 1993 to 2016 period, and I have developed this long-term average to see whether there's any correlation between the snowmelt and the sediment phosphorus, organic phosphorus, and the soluble phosphorus transport. And in this case, during the melt season, we're talking about April, mainly March and April here, the highest snowmelt would occur in the northern and central part of the watershed, and then in turn, the export of these different components would sort of coincide with this timing. And then here we are talking about the growing season, which is the phosphorus uptake. So the main time of the phosphorus uptake shows up from June to August, and they are also concentrated in this area. So the brighter the color is, the higher the value. And that means during summer, the major source of phosphorus loss is through plant uptake, which is pretty obvious. Now, this is one of the key findings I did. This part is the decadal variation. So basically what I did is I separated the entire study period into two segments. The first one goes to 1993 to 2000, and the second one goes to 2001 to 2016. And I want to see if there is any change of the timing of the snowmelt. So basically all of these figures for all counties. So I studied all of these features on county basis. Basically for all the counties, we can see that this is a probability distribution function, which is telling you which date is most likely to occur on the first occurrence of snowmelt. So the blue shaded area basically represents the latter half of the decade, and the red area is the first half of the decade. This potentially suggests that there is a likely about 2 weeks shift towards the earlier end of the earliest snowmelt event. So on top of that, there is also a analysis on the frequency of the occurrence of snowmelt, and we have also observed a slightly bit of increase in the frequency of snowmelt for basically all the counties, and that would actually result in an increase of the organic phosphorus transport, sediment phosphorus transport, and the solution phosphorus transport. So these phosphorus transport are the potential transport that is exported from soil to the water body. So then what I looked into is the fertilizer application rate. So we have, if you look at the figure here, we have two bars. The left one is the soil phosphorus pool. That's the soil available phosphorus. And the right-hand side is the phosphorus fertilization. So in our study area, there are 3 scenarios, and all of the county falls into either one of them. So bear in mind that their application rate are relatively close, but yet we can see different trends. For example, we can see the first case, which is a relatively balanced soil phosphorus pool. an increasing trend of the soil phosphorus and then decreasing trend of the soil phosphorus. So that would suggest that there are other natural processes that impacts the soil phosphorus, and that's yet to be discovered. So, and this result actually just came out last week, so I'm going to further explore this. So here are some implications. So the first implication is that we're going to see earlier and more variable snowmelt. Then we are also observing a decadal phosphorus drawdown under certain scenarios because of imbalanced MP inputs. And on top of that, we can see some winter and spring P pulses due to the snowmelt that could potentially cause the downstream pollution, mainly caused by the increasing snowmelt events. And then also there are model limitations. They're mainly surrounded on data, either the data accuracy or data scarcity. So in conclusion, for now, we know that there is a hydrology and biogeochemistry coupling, meaning that a lot of these hydrologic parameters are sort of impacting the seasonal phosphorus mobilization and the long-term phosphorus depletion. Also, there's a shifted timing, which means that the snowmelt is being moving forward, and that could impact the available phosphorus in the soil, that could intensify the investments from the farmer's side. And finally, there is adaptive management required, which means that we have to align the fertilizer application rate with the with consideration of the water quality. So that's it. Thank you very much, my supervisor, Dr. Morne Farmazi, and all of our collaborators. Thanks.
So we have time for a few questions.
Thanks for a great talk. Really enjoyed it. And you mentioned some of the improvements in SWOT. I have a question about spatial variation within the field. And it may not be simulatable based on sort of model structure and so on, but how important do you think, we see 2 to 3 fold variation within a field and even larger across fields. How important is that in understanding the dynamics of the system, that sort of fine scale spatial variation?
Well, I think that's a very good question. I think that's actually part of the limitation because what has been improved in the SWOT model is the algorithm that captures how phosphorus is being mineralized. And so basically the mineralization and the immobilization processes, that's not a problem. The problem is the spatial resolution because it's so variable in our case. So that actually depends on what's your end goal. So what I think is that depending on if you want to focus on a plot scale study, farm scale study, or like a large watershed scale study. So let's say if your goal is to, for example, give suggestion to farmers for a particular plot, then in that case, you probably gonna need a very high resolution, very fine resolution of your input data. So that includes a lot of aspects, for example, the climate, which may be, pretty uniform in a very small area. But then in that case, you're gonna need the soil information, you're gonna need the land cover information. So, it all depends on what's your end goal. So in my case, this study aims to look at the larger scale. So I have to somehow sort of assume like a homogeneity for each sort of like subsection that I'm looking at. But if I do have a need to put more focus on a smaller scale, then I have to increase the resolution for sure. So the processes are well represented, but the spatial resolution of the data is definitely, important, and that definitely impacts the accuracy of the simulation.
Thank you very much.
Thank you.
And our next speaker would be from University of Alberta.
Good afternoon, everyone. My name is Couture. I am from University of Alberta, and I work with Dr. Moira Farmazi, she is there, and Dr. Cameron Kyle. So today I'd like to talk about sensitivity of mainly plant carbon inputs to the hydroclimate change in the temperate grassland of Nestle River Basin. So before I start, I'd like to give a bit of background why grassland and why we care about soil organic carbon. So as we know, here many people are from the ecology background. So any ecological system would has lots of functions and lots of services. So some of them are like ecological regulation and the provisioning and cultural services. And we talk about this ecosystem functioning. The soil organic carbon is one of the most important indicator. So because it provides certain and many soil properties, and also supports many functions, and because of that we have outcomes from erosion or flood control to the climate mitigation. So I'd like to more focus on the climate mitigation through the carbon sequestration. So if you see globally, uh, there is a carbon sequestration opportunity of about 2.3 to 7.3 petagram for the biodiversity restoration, and about 0.15 to 0.7 petagram for improved grazing management. And this also comes with the long turnover time, and it's often protected from the disturbance like fire. But when we talk about this potential, we are mainly talking about the degraded grasslands, mainly in the near the equator or the lower latitude regions. And it's believed that the Northern American grasslands are generally in good condition in terms of potential. But when we say good condition, how it depends on how we are saying it. So like how does soil organic carbon interact with this region's changing climate? And the humans. So are there some regional ecosystems are more vulnerable than others? So before we go into that, let's see how soil organic carbon cycle works. So if you see from global perspective, so here I'm showing 3 different carbon pools or the ecosystems. Of course, one is the atmospheric carbon, and then there's a terrestrial or the soil carbon, and there's aquatic carbon. So in ocean is the largest pool of the carbon, but when we talk about generally terms of terrestrial and the atmospheric carbon, the soil carbon holds about like 2,400 petagram, which is like 3 times of the atmospheric carbon, and most of it stored in the top 1 meter of the soil. And when we talk about the climate change, this is small number which all is causing it, like 4.7 petagram. So we can imagine even the small export from this soil carbon, if it goes back to the atmosphere, what would happen, right? So that's why it's very important to understand what's happening about in a soil carbonic dynamics, how changing climate is affecting it. So now if we see the soil organic carbon cycle from at the micro scale, from the mass balance perspective, as any mass balance system would have a 3 component, right? Like the input, output, and the balance between both of them will determine the change in storage. So as an input, we have mainly the plant inputs, which is like residue, root, and other dead root, other stuff, and animal as well, in terms of manure or the dead animals, which would enter into soil, will go through different physical and biochemical processes, and will transform into mainly the 2 pools, which are POC, which is particulate organic carbon, and MAOC, which is mineral associated organic carbon. And if it is a like kind of we see this as a soup. So if it is like a kind of soluble or even insoluble, it will be like DOs, which is dissolved organic carbon. Now as an output, we'll have a main component is the soil respiration, and couple of hydrological export as well, in terms of forms of erosion, leaching, and percolation. So balance between this input and output would determine the storage. Now let's see what determines this balance. So if you see the stabilizing mechanisms are mainly the microbial physiological inhibition, microbial limitation, metabolic limitation, and microbial excess constraint. And these are controlled by mainly the direct climate controls and indirect climate controls. So as we know, so it's why it's very important to see how the changing climate would impact this whole carbon cycle, right? So which kind of forms our overall objective. So we are mainly focusing on to assess the interactive impact of snow drought and grazing practices on watershed soil hydrology and plant carbon input in temperate grassland of Canadian prairies, and then what are the seasonal transitions and the post-drought recovery, which forms our objective as to simulate the effects of the changing soil moisture, evapotranspiration, soil freezing through cycles, snow melt, runoff and the runoff on the spatio-temporal variability of associated fractions, and also to assess the effects of grazing management options on the plant productivity and associate in different ecoregions, and to assess if there are some kind of adaptation strategy we can implement to enhance the snow drought resistance and carbon sequestration under future climate scenario, and understanding the trade-off between the plant carbon input and the food security. Now, to achieve our goals, we are using a tool called Soil and Water Assessment Tool. And I mentioned carbon improved because we are working on improving the existing carbon module. But I'm not talk about this in this presentation. But if you're interested, we can talk about it after the talk. So in this model, it has mainly 3 components. One is hydrology. There's a one plant carbon phenology component. And there's a nutrient cycle for the carbon, nitrogen, phosphorus, and which has the feedback and the trade-off mechanism between them. There's input data from the weather module, and also has the operation module, which the land management module, which can do grazing management or irrigation, all sorts of land management. And it also has a feedback mechanism to channel processes. So if you see from the water security perspective, so if you want to assess what kind of export is happening to channel, and in terms of water quality, it also has that mechanism to do that. So for our study focus is on the Nelson River Basin. So I guess most of you will be aware of the basin, so I won't talk about it much. So far, we have carried out the stream flow calibration validation, the crop yield calibration validation. We are in a process of doing carbon mostly verification because of the scarcity of data. But to address that, we are focusing on doing the calibration validation for the above ground biomass, and if it's possible, even the below ground biomass. And we are now working on the soil temperature calibration validation as well. Now, as I mentioned, we wanted to see the interactive effects of the snow drought, and what is the response of plant carbon input, and how the summer rainfall would play any compensatory effects or not. So for that, we are trying to come up with the kind of new approach. So for that, we have come up with these 3 indexes. We have namely snowpack index, summer rainfall index, and the plant input index. So I'll take the example of the snowpack index. What is it? So if we see at these 2 graphs at the bottom, so the graph on the left is showing the monthly variation for the last 40 years for the month of April. So how we have calculated is the 6 month snowpack mean from the October to April. So, and from that, we will determine what is their variation from the median. If it is the value is above median, it would be range from 0 to 100. If it's below the median, it will range from the -100 to 0. So it would, if it is 100, it's like extreme wet condition. If it's a -100, it is a extreme drought or the dry condition. So similarly for the summer rainfall and the plant carbon input index as well. But here only the 2 changes are, these are from April to October, which is kind of growing season. And instead of it's a mean, it's an accumulation for the 6 month. Now, in terms of the verification, so so the figure shows here in the point is the observe SOC data for the top 15 centimeter of soil, and this is a simulated data in the raster form. So it come across as a good, if there are a good agreement. So because it's already like a physics-based model, but with and we believe with our calibration validation, it will improve from here as well. Now, if we see in terms of results, so here I'm showing 2 graphs for the 2 ecoregions, which is mixed grassland and mixed moist grassland. On the x-axis is the snowpack index. On the y-axis, it is summer rainfall index. And the points are from this ecoregion subbasins or HRU for 40 years. So, and they are color coded with the plant carbon input index value. So in generally speaking, we can see it's mainly trade from like blue to red in a general. So we can see it's more like dominated by the summer rainfall values in both region. But if you now start looking at start with the corner here, so if we have an extreme snow drought and the extreme summer rainfall drought, which makes sense here, so which is like kind of reddish, so like higher red, it just show that higher reduction in the plant carbon input as well. As we go up bit top, now it's become more interesting. So here, what exact is showing here? So even if we have a moderate or normal summer rainfall, but the snow drought or like extreme to the moderate snow drought would it won't compensate that effect. So we can see there's a reduction in plant carbon input even if you have a good summer rainfall year. Uh, so this is kind of interesting to see. So that is our these are our next step to understand why we have this varied response. So for that, we want to now look more in detail, like why and how this underlying processes are changing and that's causing it. So we want to focus now more on the freeze and thaw process change, snow melt process change, like, and how would impact the soil moisture regime, eventually the plant carbon input and the carbon stock as well. These are our next steps. And I would like to conclude my talk with this, with some conclusion and some questions. So the plant carbon inputs are adversely affected by the change in the snowfall and summer rainfall precipitation and caused by climate warming. But why do plant carbon input and SOC have different sensitivity to hydroclimate change across the different ecoregion? And what are the underlying processes? And what about future scenario? Like once we have a more intense change in the hydroclimate, how will it impact that? And how does hydroclimate respond to various management practices? And also what will be implication for the aquatic ecosystem as the export will also increase or would change? So that's one of the goal from the water security perspective. And I like to conclude my talk here. Thank you for listening. And this is a closement. Thank you to research agencies as well. Thanks. I'm happy to take a question.
Any questions?
Thanks. Really interesting work, and it's nice to see the carbon modeling advancing at a large scale. I think you may have answered the question on the last slide in that it's a next step, but I'm super curious about how much DOC export or concentrations in runoff should be expected to change, or how much temporal variation you've seen over time.
So we have some results, but we did not really analyze. So what we are saying is bit varied response. So across the region, there's a change in the snow melt regime as well. And because of snow melt regime, there is a propagation happening. It's not sudden change in the export, but in some year we found in some region, if there's a very rapid snow melt change, it's causing immediate effects on the export. But and what we are expecting in a more of the region is more of like propagation, like year by year change and accumulation of in the soil, then it exported as some certain high extreme event comes and sudden release kind of thing. So yeah, but we are still have to work more on it, yeah, I guess.
Thank you.
Yeah. Okay. Okay. Thank you.
Welcome to the next speaker, Alaya Mendy.
Hello, everyone. Welcome to my presentation. I want to share with you what we found so far about the impact of continuous cover on phosphorus export at the watershed scale in agricultural watersheds on the Canadian side of Lake Erie. So I'm going to start with a little bit of background. So you know that excessive phosphorus loading into Lake Erie caused pervasive eutrophication problems, and actually research shows that about 70% of phosphorus loading is coming from agricultural activities. And there are several binational agreements that is promising to reduce phosphorus loading into Lake Erie. There are several agricultural-based management practices in place, including cover crops that shows it can be used as a mitigation strategy to reduce phosphorus loading and also as a strategy to protect soil. So my focus would be on cover crops. So what are cover crops? Cover crops are secondary crops on the field, so it's different from cash crops that you will have during summer. It's not necessarily intended for harvest, although it can be harvested as well. But the main idea is to keep it in non-growing seasons over winter, so it can be used for reducing soil erosion and runoff. So I wanted to know how I can incorporate cover crops into phosphorus loading models. So for phosphorus loading models, there are two main approaches, process-based models and data-driven models. And actually, there is an over-reliance on process-based models. Literature shows that over 70% of studies used SWAT alone as the modeling tool in their phosphorus loading models. And when it comes to cover crop, we had this very nice study by Martin et al. 2021 that is in US side of Lake Erie, and it shows that cover crop can be effective in watershed level to reduce phosphorus load. But what I want to do is to use a data-driven model to first of all have it as a process, as a phosphorus loading model, and also I wanted to add a cover crop into that. So so the tool that I'm going to use as my data-driven approach is generalized additive models, or GAMS, and it's suitable in dealing with complex and nonlinear systems, and it accommodates different prediction models. So I'm going to repeat the research gap that we have here. Actually, is the strict structure of the process-based models that you're dealing with initial assumptions in these models, and when the data is scarce, then you cannot really sketch critical watershed processes. Another thing is we wanted to have an additional approach, which is data-driven, to eventually compare, complete, and validate the results of process-based models. And I actually break the over-reliance on the process-based models. So I'm going to start talking about what was the data that I have for my research. So I had water level data every 15 minutes. I had very good biochemistry data, typically measured 2 times per week on average. And also I had cover crop data. So here I'm gonna show you the very base model that we had for phosphorus loading without any cover crop. So you get familiar with the results of GAM. So here, very, very basic model. So I have the predictors are day of the year, discharge, and daytime. So day of the year captures seasonality. Discharge, obviously, very important predictor when you want to predict phosphorus flux. And daytime as a numerical input, so you're capturing trend. On x-axis, you have different values of your predictors, for example, the discharge or day of the year, and on y-axis, you have partial effect that actually shows the effect of that specific particular specific predictor that you had. So I'm gonna start showing you the study area that I'm working with. It's in Southern Ontario, Lake Erie watershed. And I'm working with 6 watersheds that are in 3 pairs. How I paired them, so these are the watersheds Medway East and Upper Medway, for example, my pair A. The 2 watersheds within this pair are similar in hydrological and physical characteristics, and one watershed in each pair had incentivized programs for farmers, so they're more encouraged to have cover crops over winter. And for this study, I'm going to focus on to show you the results that I had for my first pair, Medway East and Upper Medway. So here I have the cover crop maps during study period. The maps that you see here, the white fields are the ones that had no cover crop, and the colorful ones had different species of cover crop. It doesn't really matter what species we have, because for now we're just focusing on the area of the cover crop, not a specific species. And so, yeah, I told you that I have water level data every 15 minutes. I had very good data for biochemistry, but when it comes to cover crop data, I had one number per year that showed the area of the cover crop within each watershed. So the GAM model is a data-driven model. Obviously, it's data hungry. And I was like, okay, when I put these data into the GAM model, it obviously crashed because it cannot really find the relationship between the outcome and predictor, given that for the full year, you're just feeding it with one number. And yeah, as I said, this is my annual cover crop numbers. And in this table, I turn them into ratio, so into percentage, so it's easier to digest for a presentation. So not only I talked about this cover crop variability, not only the GAM model crashes when you do not have really this variable nice cover crop area, another problem is that cover crop actually goes through phases. These images are cloud-free sentinel images from 2022, and the red outline actually shows the fields that I had cover crop based on my survey data that I had access for. And as you can see, okay, image 1 is August and September, then November and December. You can see that how the colors changes and the grainness changes, and cover crop goes through phases through each field. So I was like, okay, how can I really capture this, these different phases, and how can I feed it into my GAM models? So I was like, okay, I should come with a cover crop proxy. And I was like, okay, I'm going to use remote sensing data. I'm going to go and use vegetation indices in non-growing months. So I used Google Earth Engine, and I calculated different vegetation indices over each field as an average monthly per field, like vegetation indices. And then I selected the modified soil vegetation indices, because then it's better in recognizing bare soils versus whatever that has had any kind of cover crops during winter. So obviously non-growing months, we considered it from October until end of May as our non-growing months. I set vegetation indices 0 in the growing months, and then I use the other months to start, how can I say, give a variability to my cover crop area. So here are the results. Cover crop area partial effects on phosphorus. So obviously I added cover crop into my GAMS model. And I looked into different species of the phosphorus, TP, DRP, and TDP. And this slide actually is easier to understand. So I turned those numbers from the GAM model into, okay, how much of effect I'm gonna see if I increase my cover crop area about 500 square meters per watershed. So it shows that, for example, for TP in Upper Medway, if you increase it by that much, the TP will increase by 10.3%. TDP will reduce a little bit, DRP as well, but all in Medway East, all of the P species will actually increase. But the field level research shows that, field scale research shows a decrease in TP when you increase cover crop, and sometimes increase in DRP. So actually our findings in watershed level doesn't really match with what we had from other like literature review and field scale research. Yeah, a little bit a bummer, but. So what I'm gonna do next, I'm gonna focus on the rest of the pairs that we have, pair B and pair C. And I'm gonna see if I'm gonna get similar results for the other pairs as well. Obviously, if the results are not similar, we're gonna look into what are the differences between watersheds and why we are seeing different results. And that's it.
We have time for a couple questions, if anyone wants to raise their hand.
Thank you. I thought it was really interesting. I was wondering if you had considered looking at any of the P inputs onto the fields in addition to whether they had cover crops or not, because depending on where they are in their cycles, you're going to be having different P inputs depending on the crops that are being grown that year.
I see. We didn't really look into P input per field specifically. What was per field that we look into was the distance from the river, like from the creek, to see if that has, like, the further the field is, it has more effect or not. But no, none of them showed any significant effect on our results, actually.
Thank you.
No problem.
I think we have time for another question.
I think I really finished early.
All right, thank you so much.
Good job.
Welcome to the next speaker, James Rankin.
Wait a little bit, we will start.
Oh, just a minute or two.
Because maybe some people want to come.
Oh, sounds good.
So we will start at 2:15. So we have a couple of minutes.
Okay, yeah.
It's good to start on time because, like, many people, because maybe they stick with other presentation, but they want to come here.
Sounds good.
One more minute.
Okay.
And you know that to use the remote control.
So just click.
Yeah. So here, if you click here, it will be laser pointer. Here. If you click here, it will be
Advance.
slide.
Okay.
If you
Go back.
would like to go back, like this one.
Okay. Perfect.
And also, like, when it will be 3 minutes left,
Yep.
I will put the paper on this one, so you know. But that's 1 minute and then 0. Yeah.
Sounds good.
It's time. Yeah.
Okay, good to go. Alrighty, well, thank you for the introduction. My name is James. Today I'll be sharing with you some of the work of my master's thesis at the University of Northern BC, looking at constructing a fine-grained sediment budget for a major salmon spawning river in the Quesnel watershed. So the photo on the left here, we've got the Horsefly River, and on the right, we've got some sockeye salmon on a spawning gravel, which, as you segue into mentioning this project is funded by the BC Salmon Restoration and Innovation Fund. All right, so I'm going to talk a bit about sediment budgets in general, go into why we're interested in fine grain material, go into the study area a little more detail, go over some research questions and themes of my thesis, talk about how we collect the data, look at some fine sediment fluxes in the watershed, go into the geochemical properties of the sediment we collect, and then some sediment-associated chemical loads, and then finish with some future directions. All right, so depending on your field of study, something like this may or may not look familiar. It's a sediment budget where we have kind of inputs and outputs coming from different kind of geomorphological components of the watershed, sinks and stores. So while I kind of study a few different kind of components, today we're just going to look at sediment discharge at the river mouth. And the reason why we're interested in fine grain material, things like silts and clays, are they're a lot more kind of chemically active per unit of weight, well compared to more coarse material, things like gravels and sands within the context of a river that are a little more chemically inert. Also with this being kind of a salmon related project, fine material is really important to understand as it can kind of get into that interstitial area between spawning gravels that salmon rely on. Okay, so here's our study area. It's the Horsefly River watershed. As you can see, it's in the Upper Fraser River Basin in British Columbia. This area is on the traditional and unceded territory of the North Secwepemc First Nation. And as a tributary to the Fraser, it supports 3 species of salmon. We have sockeye, chinook, and coho. And each of these 3 populations coming from the Fraser are listed as either threatened or endangered under COSEWIC. So that mixed with kind of a history of flooding and erosion, some recent wildfire, as well as land uses. There's a lot of forestry and some mining. So it kind of makes for an interesting area to study this topic. Okay, so our research question we're going to look at today is in blue here on the right, and that's what are the current fluxes of suspended sediment and associated metals and nutrients that are eroded and transported within the upper reaches to downstream sites in the Horsefly and then enter Quesnel Lake. And so how we're going to answer that is through river water and sediment collection. Okay, and so how this works is we've got a couple instruments here installed at each of our 3 sites. We've got on these, inside these green boxes, we've got ISCO water samplers, and how they work is we have them programmed to take a sample every 24 hours, a 1 liter water sample that's kind of coming from the kind of mid water column where the suspended sediment load is, kind of above that kind of bed load. And what we do with each bottle, so you can see in photo 3 there, there's 24 bottles stored in these trays. So what we do with each sample is filter that down, and we're left with a weight. And that's, so we'll see on the next slide is SSC, which is suspended sediment concentration in the unit of milligrams per liter. And so that's where that comes from. And then we pair that with our time integrated sediment collectors, which is kind of a fancy word for these PVC tubes that we have installed in the river to collect fine material. So they have a small opening at the front and the back, and we install them facing upstream as water passes through. Time allows for the water to slow down, and then sediment is collected. So this kind of gradually happens during the 24-day period when we go out to install the equipment, and then when we head back, we kind of switch out the bottles and collect our kind of bulk sediment material. All right, so as I mentioned, we've got our SSC and suspended sediment concentration in red here, milligrams per liter of daily value. And then in blue here, we've got our stream flow in meters cubed per second. So we can see at our kind of upstream site, a downstream site, and then a key tributary that kind of feeds the river. We're seeing our highest daily values as expected during the spring associated with that snow melt and the spring freshet. So we can see throughout the kind of open water sampling year, stream flow really drives the concentration of suspended sediment. We're seeing our highest daily values again in the spring, and then kind of a lull in July and August, aside for one kind of few events at the downstream site in August there. And then kind of, yeah, following that lull period, we're seeing some peaking values in the fall kind of associated with kind of late season precipitation events. Okay, so now that we've looked at kind of volume of water and concentration of sediment, we can now determine a suspended sediment load. So this is tons per day at our downstream site. and for each of our 3 sites, and we can see that they kind of follow the same trend where our highest daily values, the most sediment is being moved. During the spring, it's kind of tapering off once the freshet kind of comes to an end, and then picks back up again with some kind of fall precipitation. And this is for the 2024 year. Okay, and now to get into kind of the geochemistry of the sediment we collected in our bulk sediment collectors. So on this top row, moving from left to right, we've got our different samples throughout different times of the year. And then moving further to the right, we've got our sediment quality guidelines set out by CCME and a few independent papers. So we've got our intermittent sediment quality guideline as ISQG, PEL is probable effects level, LEL lowest effects level, SEL is severe effects level, and then our regional background levels. So we'll see that manganese is bolded for all but one of the kind of samples throughout the year. And the reason for that is it's exceeding the severe effects level. So it's getting past that kind of benchmark guideline of concentration where we can assume there's some type of kind of impact on the aquatic biota in the system. Phosphorus as well is kind of high at different times of the year, kind of some variation from sample to sample, potentially due to kind of just natural nutrient cycling. We're seeing it exceed the lowest effects level, but not quite get to the severe effects level the same way that manganese is. And then our metals, particularly chromium, copper, and zinc, again, are kind of getting past that first set of guidelines. And there's some variation throughout the year, particularly spring and fall being our highest values. And then, passing that first set of guidelines, not quite getting to the severe effects level, but something to keep an eye on moving forward. Okay, so now we've kind of looked at 3 types of data: the total volume of water, concentration of suspended sediment, and then our geochemical properties of the sediment. So this is for our downstream site. So we've just looked at our total sediment in blue on the top left here, and that's tons per day of total material. And then our kind of, I just put these boxes here for kind of some added ecological context of when the fish are in the river. The salmon really kind of rely on this time. So just put these boxes here for some context. And then for our metals, we've got in kilograms per day, our zinc, chromium, and copper. Our highest daily values as expected in the spring. And then we're seeing that same lull period and then peaking again in the fall. This is kind of pattern is also followed with nitrogen and carbon with a little higher values with nitrogen in the fall. What's interesting here is that with phosphorus and manganese, particularly with manganese, our highest daily values are in the fall, so in kilograms per day. So this could be kind of due to natural nutrient cycling, something that kind of a longer term study could shed light on, or more kind of extensive kind of soil sampling campaign could answer this. Moving on. Okay, so some future directions of the project, we'll be looking at assessing stream flow as a driver of nutrient flux. So I've just put these 2 hydrographs here to kind of show that over the 20-year period, we have stream flow data that 2024 was much less than average. So kind of making some speculation or like anticipation work of looking at what types of nutrient flux could we see with potentially up to 3-fold the stream flow that we saw in 2024. And part of that will be using a variable infiltration capacity model to look at kind of projections of what stream flow in the future could look like with kind of changes in snowpack and changes of kind of more precipitation as rain than snow and some kind of uncertainty there. I'll also be looking at completing the sediment budget, so building out kind of similar work, looking at kind of the total mass and then the geochemical properties of fine material stored in the channel bank and floodplains. And then just as a follow-up study, we may do a little bit more looking at sediment fingerprinting and sourcing to kind of determine the sources of the metals and nutrients that we're finding in the channel. So kind of determining where they're coming from through our different kind of geomorphological kind of components of the watershed. All right, I would like to finish by thanking my thesis supervisors, Dr. Phil Owens and Farhan Ali. Again, the Department of Fisheries and Oceans and the BC Salmon Restoration and Innovation Fund, and then the Quesnel River Research Center at UNBC. So with that, I'll hand it back over to our chair. So thank you.
Great.
we have plenty of time for questions. Seat 1 and then 2.
Thank you. So I know you said in the future directions you were going to look more at the sources, but I just had a quick question on like, do you have any ideas what might be causing the elevated manganese in like the fall, or like what type of pollution would be causing it?
Yeah, it's a good question. We've done some like soil sampling to see just like where things chalk up to. It is kind of a little bit elevated in the channel, especially in the fall period. One thing that could kind of answer that question is that in the fall, especially, there's a lot of groundwater input in this watershed. So that could be a driver of it, but it would take like a little bit more kind of, yeah, soil sampling and potentially some like groundwater sampling to kind of answer that fully. But yeah.
Would it be possible to go back to the like comparative graph where you showed the 3 streams with the discharge and the sediment concentration? I was wondering about Muffet Creek, whether basically comparing the discharge, which seems to be lower than the 2 others, but on the other hand has a much higher sediment concentration. What do you think causes this compared to the other ones?
Yeah, it's a much smaller flow, as you mentioned. So I think during that spring freshet, I think just because it is a creek versus kind of a much larger watershed kind of drainage area for the other 2 sites, I think that just a lot of the water kind of, the spring melt happens like very quickly. So a lot of that sediment is kind of moving pretty much all at once. It's a much shorter kind of freshet, so it's a lot more concentrated, kind of similar to the stream flow. So yeah, does that answer? Yeah, okay.
Time for any more questions?
Okay.
All right, thank you so much.
Welcome to the next speaker, Joan Foster.
We will wait for 2 minutes and then we will start.
Okay, cool.
Just on time.
Can we go to the first slide? Or I can just do this. Yes.
And we have 3 minutes left. I will put this paper on this.
Okay,
so no 3 minutes and then 1 minute and 0. Because like under the still they have presentation, maybe people want to switch, so they know that they come like 2:30, so it will be your talk.
Yeah.
So they don't come already on the third slide on the first.
Yeah.
Almost here, so just a few seconds, a few more seconds. When you wait, the time is so small. Okay.
All right, thanks everyone. My name is John Foster. I'm from the Water and Ice Research Lab at Carleton University and supervised by Dr. Mary Richardson. and today I'm going to be talking about my some early results from my MSc Geography thesis work up in the central Yukon. And just to provide before I start getting into the slides, a really quick overview of what we're doing is we are taking an empirical modeling approach to predict total suspended solids in the small streams and rivers of the Stuart River watershed using the watershed proportions of disturbances, so large surface disturbances, to predict the total suspended solids. So the Stuart River watershed falls almost entirely within the Nacho-Nyack-Dun traditional territory in central Yukon in the northern boreal mountains. And this work is a collaborative project with NND, Nacho-Nyack-Dun, which was co-developed between them and the Carleton University Department of Geography. My work is part of this larger project called Monitoring and Mapping the Cumulative Impacts of Surface Water Quality in the Stuart River Watershed, which is specifically focused at looking at impacts from mining and other climate change related disturbances. So here we have a map of the Stuart River watershed. The drainage is from the west to east. It's about 50,000 square kilometers and is a major tributary of the Yukon River. The anthropogenic surface disturbances are in brown. Recent wildfires in the last 5 years are in gray. And then the yellow dots represent our sampling sites. And the watersheds of each of these sampling sites are independent in that there's no nested watersheds in the study. Which was important for the assumptions of the ordinary least scales or least squares linear regression modeling that we're doing. Oops. So there's a lot of community concern in the Nacho-Nyack-Dun First Nation with anthropogenic surface disturbances especially. There's a history of over 100 years of placer mining in the region, as it's kind of the next area over from the Klondike. And there's lots of these placer mines throughout many of the river and stream valleys, which are built right in the near stream zone and often include moving the stream and creating lots of large piles of overburden and vegetation removal, resulting in many different pathways to increase suspended solids in the streams. And these streams form a very important habitat for fish species such as grayling and salmon. So there's a lot of concern about the impacts to those fish. So furthermore, there's natural disturbances, of course, in the region, such as large wildfires, which are shown to be increasing in both intensity and frequency in the boreal forest. Here we have a photo looking up the Haggart Creek watershed towards the Eagle Gold Mine in the distance there. And on the left is a recent wildfire from the summer of 2023. So a lot of these disturbances are occurring sort of in the same watersheds. And so the cumulative impacts of them are important to consider when we're trying to tease out the signal from the anthropogenic disturbances. So the primary goal of this work is to support evidence-based land use planning in the Nacho-Nyack-Dun traditional territory. As part of the 1993 final agreement, which they signed with the federal and territorial governments, there's a land use planning process that is being promised to occur, but which has not yet happened. So the specific objectives of this work to support that goal are to try to develop local land use indicators of water quality, highlight priority areas for conservation, and produce predictive water quality maps. So the research questions that we were asking are these two. So what is the relationship between anthropogenic surface disturbance and water quality? And how does the spatial distribution of disturbance affect this relationship? So it's kind of a composition and configuration pairing here. So we've got the composition being the watershed disturbance proportions, and then configuration, such as where the disturbance is located relative to the stream network. So the methods that we used, we began by selecting 40 stream sampling sites across disturbance gradients. So from no disturbance to as much disturbance as we could find for those two types, anthropogenic and recent wildfire, while also kind of controlling for watershed size. The watersheds range from 10 square kilometers up to about 550, and they're limited to sort of Strahler order 3 to 5 stream sites. We also wanted to make sure that the sites were relevant to other NND monitoring efforts. We performed 3 short synoptic water sampling campaigns in summer 2024, where we tried to visit all the sites as quickly as possible in order to capture them within sort of the same hydrological regimes. We collected a whole bunch of different water quality analytes, which we will continue to look at and work with, but this presentation is just focused on the TSS component of this. So to prepare that TSS data for the modeling, we filtered out some sites that had some observation issues related to upstream beaver dams and such, as well as 2 outliers. To account for number of values which are under the detection limit, we use what's called regression on order statistics imputation in order to then calculate median value for each watershed over that summer. For the geospatial side of this, we used the Yukon government's very detailed anthropogenic surface disturbance data set, supplemented by student Megan Elliott, whose work included digitizing many new disturbances which were in that government data set. And as well, I manually digitized a bunch of disturbances using PlanetScope imagery that weren't found in this data set. In this work, we're treating all disturbance classes the same, even though we do have information about different types of disturbance, such as placer mining versus transportation. So that's something we will look at further in the future. Wildfire burned areas, we characterized by using the Government of Yukon's fire history map. But in order to get a little bit more detail within those boundaries, we incorporated the normalized burn ratio derived from summer 2024 Sentinel-2 imagery. And then we needed to then determine disturbance proportions upstream of the stream sampling sites. So we used this, what we're calling landscape accumulation, which is a method of using flow accumulation to simultaneously calculate these proportions across the entire study area. And just a note, all the disturbance proportions, sort of from here on out in the presentation, you can think of as logged disturbance proportions. We found that improved all of the models that we looked at. So in order to sort of answer that second research question about how the configuration of disturbance affects these relationships, we're following the methods laid out in Weller 2023, where they sort of formalized the use of distance weighting functions to represent the decay of influence that land cover has. So land cover far from a stream, you would think probably is going to influence the response variable less than land cover right next to the stream. And so we calculated these distance bands around all the streams using downslope distance to stream as the sort of metric for that. And then within each distance band, we then aggregate the total number of pixels as well as the total number of disturbance pixels, so that we have that proportion story sort of across the entire watershed from the streams outward. But rather than just sort of making a priori, decisions about the distance weighting parameters, we used a grid search optimization to fit the distance decay functions to the data. So here we can see across in the plot on the top, we've got the distribution of disturbance from the stream network outward. So we can see anthropogenic is very close to the stream, wildfire is more widely distributed. And just to show what these distance weighting optimization thing looks like. So an unweighted land cover regression, the proportions are treated as the same, like the land cover is treated the same regardless of its position in the landscape. So on the x-axis distance, on the y-axis is the weight, and it's just the weighted is just 1 the whole way across. But we can model the decay of influence using various different functions. So here we have our anthropogenic and wildfire distance-weighted regression formula, which we then run through the function optimization to figure out what distance parameters best represent the data. So here we have the results. So looking at just an unweighted model of anthropogenic disturbance alone, which is sort of the main disturbance type of interest, we can see end up with a predictive accuracy of with R-squared adjusted of 0.3. When we add in wildfire unweighted, we end up with a quite a dramatic increase in the predictive accuracy with a leave one out cross-validated R-squared of 0.56. And then once we add in the distance weighting, this model in the bottom row is the best model that we fit. Both the R-squared adjusted and importantly, the leave one out cross-validated score increases even further. And important to note here too that per unit area, as indicated by the slope terms, anthropogenic disturbance has a greater influence on the observed TSS than wildfire. Oops. So on the left, we have our optimization surface showing a pretty narrow spot there where those distance decay parameters give us the best leave one out R-squared. And then on the right is our one-to-one plot showing a pretty good fit of our TSS observations and with the dot size representing watershed size. So we can see, that's a pretty good representation of different watershed sizes across that line as well. So that gives us good confidence to sort of move to developing predictive maps of TSS at unmonitored locations. So this is an example of what we're looking to do. This is that best model applied to the entire stream network. And in conclusion, there's strong statistically significant relationship of observed TSS to anthropogenic disturbance. Controlling for wildfire results in a much higher predictive accuracy. Per unit area, anthropogenic disturbance has a stronger effect on observed TSS and wildfire. And importantly, the spatial composition and configuration of disturbance within the watershed matters significantly. So big thanks to all the members of the NND Lands Department for getting us out in the field and collecting all the water data and providing local knowledge that would have been, that was just absolutely indispensable. And my fellow students and colleagues at Carleton, as well as other partners that we've been working with. So, thank you very much.
Thank you so much. Do we have any questions?
Thank you very much. So my question is, if you want to apply similar approach to other watersheds with different settings, such as agricultural watershed, what is your suggestion? Would it be the same procedure or what kind of?
Yeah, I think absolutely. This, the Weller 2023 paper on using distance weighting as part of the regression procedure for relating watershed proportions of whatever land cover to an observed aquatic response was written in a way to suggest that this methodology is widely compatible with relating any types of land cover to aquatic response. And I could see even using benthic macroinvertebrate indices as the response variable, and then say agricultural land as the predictor in order to see what type of associations are there. And while it didn't have, there was that heat map showing anthro and wildfire proportions across the distance bands. But next we want to use that spatial location information to investigate further about how the location of these land cover types are influencing the water quality. So their paper has lots of great figures that further expound on that concept.
Great, thank you.
Thanks. I was flagged for another.
Thanks, John. Great presentation. And you've probably considered this, but can you get the time of disturbance in this model at all? And do you think that has a big impact? So time since fire, time since placer mining, something like that?
Yeah, so with the wildfire, that was one of the purposes of using the normalized burn ratio, because as the forest regenerates, we get lower NBR values, and that's what drove me to do that, because just the gross boundaries weren't very representative of what was going on. So that kind of integrates time to a certain degree. With the anthropogenic disturbance, the Yukon government data set doesn't have a time appearing on the landscape, but there's studies that show long sort of consequences to anthropogenic disturbance well beyond when you would maybe even expect it to continue. So yeah, I would love to be able to investigate that temporal thing further, maybe through some sort of change detection, pushing those pixels around.
All right. Thanks.
Thank you.
Okay. Thank you. That was our last speaker, and we are going to close this session. And thank you very much for being with us during the part 2 of our session. And we would like to invite you tomorrow for our part 3 of our session. It will start at 10:30 a.m. in the same room as here. Okay. I hope we will see you tomorrow as well. Thank you.